Welcome back. This week, we are going to extend on what we did last week with Riemann sums to talk about definite integrals and tie them back to the notion of antiderivative that we worked on week 1. So just a quick recap. If we start with a function, and we ask the question, what is the area under the curve between points A and B? This area is defined to be the definite integral from A to B of f of x dx. Now, in the homework last week, you had to find these values using geometry or approximate the values using Riemann sums, either left-hand Riemann sums, midpoint Riemann sums, right-hand Riemann sums, or trapezoid rules Riemann sums. But generally, the construction looks something like this. We split the interval AB into n many pieces. And each one of these intervals had size delta x. We labeled x sub 1 as A, and we went all the way to x sub n plus 1. And then for each one of these intervals, we chose a single point inside. I'm going to call it x sub I star as the representative of the ith interval. And then what we do is we build a rectangle over that interval to the height f of x sub I star. And then if we have enough of these rectangles, we add them together, and it gave us an approximation for the true area. Well, what happens is if we let n get bigger and bigger, the size of each rectangle shrinks. At infinity, it becomes just a straight line. If we add together all these straight lines, it gives us the actual true area under the curve. And so that becomes our definition. We're going to say this is the limit as n approaches infinity of the sum, where I goes from 1 to n, of f of x sub I star times delta x. And as a limit, this will converge to this area as long as our function is continuous or well enough behaved. This is important because it tells us that what the antiderivative is, what the definite integral is this area below the curve. Now, mathematicians do something very strange. Once we understand this area to be this object, this definition, we're going to create a new object and ask what kind of properties it has. So here's how we create the new object. Yeah, I know. It looks an awful lot like the object we were just looking at. Same function, f of x, same interval a to b. This time what we do is we're going to start at a, and we're going to choose any value x between a and b. And then we're going to define a function to give us the area below the curve between a and x. And so we're going to define it this way. Let big F of x be exactly the area below the curve between a and x of therefore f of x dx. This is a function of x because as x changes, the value of big F changes. So what big F is here is literally a value of area below the curve. Now here is the power of calculus. This is what makes everything fly, everything that you've learned come together. This is called the fundamental theorem of calculus. the part one says this. F of x defined this way is differentiable and its derivative, f prime of x, is exactly little f. This function here is the derivative of big F, the area function. This is hugely crucial because it ties back together the notion of definite integral, which is an area, it's a geometric object, and the notion of antiderivative, which is an algebraic construction that follows rules that we've learned to do and know what they are. And this connection between algebra and geometry is the heart of what gives calculus its power. The fundamental theorem of calculus says something else that is actually what people usually think of when they think of the fundamental theorem of calculus. And it says this. So part two. So if little f of x is continuous on the interval AB, and big F of x is any antiderivative of little f, then the definite integral from a to b, the area under the curve of little f of x dx, can be computed by plugging in the endpoints into big F and subtracting. So the area is just going to be given by big F at B minus big F at A. This is huge. This has applications absolutely everywhere. And I'm going to show you a couple examples in the next video. We're going to use this when we're talking about relationship between position, acceleration, and velocity. We're going to use this whenever we're trying to find areas between curves, areas between two curves. We're also going to use this to take derivatives of more complicated functions. Functions that look like this, but we can apply the chain rule to find the derivative and evaluate it in particular places. So we're going to make use of both pieces of the fundamental theorem of calculus. And most of the problems that you're going to be doing this week are going to ask you to use either this form or this form of the fundamental theorem of calculus. So have some fun, and I'll see you in the next video.